Imagine a world where the organ donor list is a relic of the past. A world where if a heart fails or a bone shatters, doctors don't look for a replacement from someone else. They simply grow a new one using your own cells as the raw material. We are learning to weave living tissue like fabric, using biological blueprints to repair the unrepairable. This is the science of tissue engineering, and it is the most ambitious chapter yet of the Research Codon. Welcome back to my channel. Today, we are stepping into the laboratory of the future. We've looked at the data of your DNA and the simulations of your digital twins, but today, we look at the physical reality. We are exploring how we combine cells, scaffolds, and signals to rebuild the human body. At its core, tissue engineering is about architecture. To grow a new organ, cells need a house to live in. We call these scaffolds. These aren't just empty structures. They are highly engineered biomaterials designed to mimic the extracellular matrix of your body. Whether we are using aligned nanofibers for skin repair or tunable hydrogels for spinal discs, these scaffolds provide the physical support that tells cells where to go and how to grow. We are moving toward biomimicry, creating synthetic environments so natural that the body doesn't even know they are man-made. But a house is useless without instructions. This is where synthetic biology and genetic engineering come in. We are now able to program cells using CRISPR and synthetic gene circuits. We can tell a stem cell exactly when to turn into a muscle cell or a neuron. By controlling the genetic switches within the cells we place on a scaffold, we can ensure the tissue matures into a functional, living part of the body rather than just a mass of cells. Cells don't just read DNA. They read their environment. Research shows that cells respond to a synergy of signals. It's not just about the chemicals we give them, but the mechanical pressure they feel. For example, in tendon engineering, we use bioreactors to pull and stretch the growing tissue. This mechanical tension, combined with biochemical cues, is the secret language that triggers tissue regeneration. When we get the stiffness of the scaffold and the flow of the nutrients just right, the cells integrate and recover with far more efficiency than traditional medicine ever thought possible. While we can grow skin, cartilage, and small sections of bone today, the holy grail, a full beating heart or a functioning kidney, remains the ultimate challenge. The hurdle isn't just growing the cells, it's the plumbing. We need to master vascularization, growing the tiny blood vessels that keep the center of the tissue alive. We also face a lack of consensus on standardized protocols. To make lab-grown a reality for everyone, we must bridge the gap between small-scale success and massive clinical biofabrication. We are no longer just victims of our biological wear and tear. We are becoming the architects of our own survival. Your body is a masterpiece, and science is finally learning how to touch up the canvas. If you want to see the protocols and the biomechanical studies I used for this episode, you can find the full research on my Telegram channel. Thank you for joining me for this deep dive into the Research Codon. Stay curious, keep those cells dividing, and I'll see you in the next decode. See you soon.